Folks, in today's class, I'll talk about the final chapter, that is the properties of the wave. Properties of wave. Now, first of all, we'll talk about how does a wave look like, and then we will talk about the terminology of the wave, and then we will talk about some of the properties of the wave too. So that's how a wave look like. All right, that's a basic representation of a wave. Now, in this wave, uh, there are certain terms which we will use, and that's called terminology. So this center line, this line which you can see, is called mean line. Okay, from the mean line, if you move in the upward direction up to this point, the peak, this is the peak point, is also called, first of all, crest, and the distance from the mean line to this crest, this is called amplitude. This is amplitude, denoted by term A. And the bottom, the valley, this is called trough. The amplitude, whatever amplitude you're going to get here, let's say this is A1, this will be the same. This will be A1 too. That's why this line is called mean line. So it divides the wave into two equal halves. Right? Now, if I take the distance, let me redraw it. If I take the distance of a, of first crest to the another crest, means the distance between two consecutive crests. That's what I wanted to say. So this, let's say this is crest 1, this is crest 2. The distance between two consecutive crests, or two consecutive trough for that matter, is called wavelength. So this is trough. So this is called wavelength, denoted by term lambda. Wavelength is always measured in meters. Amplitude is also measured in meters. This is wavelength. This is wavelength. They both will be equal. This is lambda. Now, we're going to talk about how does wave behave. So properties of the wave. So let's say we have this wave. Another wave is like this, in which trough comes first. If the crest of first wave meets the trough of another wave, that's a wave 1, and this is wave 2. If the crest of first wave meets the trough of the second wave, or the trough of first wave meets the crest of the other wave, then these two waves will try and cancel out each other at that particular point. Only at that particular point. I'll tell you why I'm emphasizing on that particular point later on too. So let's say this is A1 and this one is A2, and I'm assuming A1 is greater than A2, means this wave has a bigger amplitude than the second wave. Now, as I said, the crest meets the trough of the other wave, then they will try to cancel out each other. The final wave which will be generated will be like this, A1 minus A2. Okay, and this is called destructive interference. Destructive interference. Now, we'll talk about the other property of the wave, that's called constructive interference. Constructive interference. So in this, what happens that, let's say you have two waves, then crest of one wave meets the crest of another wave. In this amplitude is A1 and this amplitude is A2. Now if the, again assuming A1 is greater than A2, this is the assumption I'm taking, and under the constructive interference they both will add up and the final wave which will be generated at that particular point will have the amplitude that will be equal to A1 plus A2. This will be equal to A1 plus A2. This is called constructive interference. Now, why I said that at that particular point? Because let's say if I draw a first wave, and I'm drawing the half wave here, and half wave is also called pulse. Pulse. Half wave means pulse. And this is another half wave, and this has an amplitude again A1, and this has another amplitude A2, and I'm assuming A1 is greater than A2 in this case. This wave is moving in the forward direction, this wave is moving in the opposite direction. So let's suppose they meet at this particular point. So at that particular point, the wave which is going to get generated will be A1 minus A2. That's the wave that will be generated at that particular point. But once they pass through each other, their size will again become exactly the same what it was, assuming there is no damping. You guys don't need to get into the into the damping. Damping is like a friction. Okay, when car is moving, there is a friction between the tires and the road, which always try to oppose the motion. Okay, in space there is no friction. In same way, when the waves are traveling, damping is a form of a friction, you can call it. Sorry. So this wave will have amplitude of A2, and this pulse, shall I say, pulse will have the amplitude of A1. Okay? Once they pass through each other. So that's why I use the term at that particular moment. Now, I'll go to the types of waves. Types of waves. There are two types of wave. First one is transverse wave. Transfer waves. And the second one is longitudinal wave. Transfer wave can be seen in a very simple experiment. Let's say you have a rope and you move it upward direction, then in the downward direction. So what's going to happen? Rope will start moving like this. So there is a generation of a wave. So that's the transfer wave. And this is just an example of whatever we were just studying about the waves. It will have certain amplitude. This will be A1, and this will also be A1. Okay. So this is a perfect example of transfer wave. That's how the motion gets transferred throughout this rope. The second wave is longitudinal wave. Longitudinal wave, the perfect example if you wanted to visualize is the slinky. So if you move the slinky, let's say this is your slinky, and if you throw it in the downward direction, so that slinky, some places it will compress, and at some places it will go under the rarefaction. So this portion is called rarefaction. In simple words, I'm going to call it as expand or stretch. So this is compression. That's how the signal gets transferred. You can also represent it in the zigzag form. So something like this, and then okay, so is this is compression. Pardon me for my diagram. The amplitude should not increase. So it's just a compression, and the amplitude should remain the same throughout the wave. So it will look like this. So here it is undergoing rarefaction, rarefaction, This is again compression. This is again refraction. That's how signal is transferred. And the example, real life example of this wave is sound waves. Sound waves travel in this format. So hopefully you understood the basics of wave. Now I'm going to talk about some math problems on the wave, and I will take this math problem on the topic of wave. So we are given a question. A fisherman anchor his dinghy in a lake 250 meters from the shore. Dinghy rises and falls 8 times per minute. He finds that the wave he finds that it takes a wave of 3 minutes to reach to the shore. How far they are apart? So we are given, oops, a dinghy, fisherman anchor his dinghy in lake 250 meter from shore. So this is, let's say, shore, and he is at a distance of 250 meters. 250 meters. His dinghy rises and falls 8 meter per minute. So this is how his dinghy rises and falls 8 times per minute. So 8 times. That's the frequency given to me for this question. So if anyone doesn't know what 8 times per minute is, you can go back into the chapter number 7 and look into the concept of frequency, and you'll find it there. And this is frequency given to me. 8 times means, and this is per minute, RPM, revolutions per minute, means that cycle is being repeated 8 times in a minute. So if I wanted to convert it into seconds, then it will be 8 divided by 60. He finds that it takes the wave 3 minutes to reach to the shore. So time taken is equal to 3 minutes, which can be written as 180 seconds, because 1 minute equal to 60 seconds. And how far they how far apart the wave crests are. So what we are looking for is the wavelength, this lambda. Now I'm going to talk about a couple of formulas which I didn't talk about while talking about the basics. So I'm going to take those formulas here. So speed is equal to frequency times lambda. That's how we measure the speed of a wave. This is the formula which we will use for measuring the speed. Previously, we were using the speed equal to distance divided by time. Now we're going to use the speed equal to frequency times lambda. So if you just carefully see these two formulas, they are literally the same thing. The idea is the same. Distance is what? Wavelength. And frequency formula is 1 upon time. So again, if you go to the chapter number 7, you'll find it there. Frequency is 1 upon time. Now in this one, and then you just take the reciprocal of time and bring the frequency into this picture, and that's going to give you the speed. So this is the formula, as I said, we're going to use. One thing which I wanted to talk about while when we're going to solve the questions on the wave, the time taken to generate the wave will be equal to the time taken for the wave to travel in the forward direction, or the speed. If I have to put it in simpler words, the speed with which the wave will be generated is the same as the speed with which it will travel. So if I am standing here, it takes me, let's say, 1 minute to generate a wave, and then this will travel with the speed of uh, it will travel, let's say the speed which I'm generating is not 1 minute, I should use the word 1 meters per second. That's the speed at which I'm generating it. So the wave will travel with that same speed, 1 meters per second. That's what I wanted to say here. Now Let's redraw the diagram because it's otherwise it's going to create a lot of hodgepodge. So this is how it is, and the distance from this point to the shore, this distance is 250 meters. 250 meters. Let me recheck the distance. Yes, correct. Now what we're gonna do is we will just try and solve this question. uh, we wanted to find this wavelength. As we set this distance lambda, I will write down the simple formula which we just learned. Speed equal to lambda times frequency. The frequency is given to me. It takes 8 times per minute. The dinghy falls and rises 8 times per minute. It means frequency is 8 divided by 60. That's what's given to me. It's given to me 8 per minute. 8 times per minute. That's why I'm dividing it by 60. Okay. So that's what frequency is. Lambda is what I'm looking for. Speed is what I am missing. I don't have the speed at which it is traveling. So let's find out the speed at which it is traveling in the water. So the shore is 250 meters away, and he finds that it takes him 3 minutes to reach the shore. So here he finds that it takes 3 minutes to reach the shore. So the speed at which it is traveling will be how much? Speed will be equal to distance divided by time. Distance is how much? Distance is 250 meter and time is 3 minutes. So 3 minutes can be written like 180 seconds. And this will be the speed at which it is traveling in the forward direction. So 250 divided by 180. That's what I'm gonna do on my calculator. So that's 250 divided by 180. 1.38. 1.3889 meters per second. So this speed will be same as this speed. Remember I told you the speed of travel is same as the speed of generation. So this is the speed of generation, this is the speed of travel. This will be 1.388 equal to lambda times 8 divided by 60. 8 divided by 60 is 0.133. And dividing both sides by 0.133, 0.133, you will get the value of lambda. So 1.388 divided by 0.133, that comes out to be approximately 10.4 meters. That's the answer for the wavelength. One thing I want to talk about here, which is really important, that it says he finds that it takes 3 minutes to reach to the shore. If it was given that it takes the wave 3 minutes to come back to the point from where it started, so means it starts from here and it takes 3 minutes to reach to the shore, and not 3 minutes, it reaches to the shore and then come back also to the same point. The total time taken for this process is 3 minutes. In that case, if that was given to us, in that scenario, I will double the distance, because the distance traveled by the wave will be not only this 250 meters in the forward direction, but also 250 meter in the opposite direction. So total distance, I'll take total distance to find the speed will be equal to 500 meter in that scenario. So 500 divided by 180 to find out the speed. Okay. So make sure you do this process, or if you don't want to do this, you can take the half of this. So if you if you want to take this distance 250 meter from the fisherman's hand to the shore, which is 250 meter, then you take the half of this time. that'll be half of 180 is 90 seconds. Okay, so make sure you carefully look into the question what it is saying. So that's it for this lecture. I will see you with another lecture. Until then, good.